In this video, we will introduce you to the dot product and explain why it's useful. We'll look at it through the example of the work done in pushing this lawn roller. Work done is often defined as force multiplied by the distance travelled in the direction of the force. The lawn roller is pushed with 10 newtons. That's not a realistic amount, but we're keeping the numbers as simple as possible. The force is acting at an angle of 60 degrees to the direction of motion. In general, we might label this angle theta. And the force pushes the roller horizontally, a distance of 8 meters. The equation for work is W equals Fx cos theta. The definition corresponds to interpreting the equation as W equals F times x cos theta, with x cos theta being the distance travelled in the direction of the force, or in other words, the component of x in the direction of F. In this example, the angle between the force and the direction of travel is 60 degrees, and so the force, 10 newtons, is multiplied by x cos 60 degrees, or 4 meters. However, you might find it conceptually simpler to think of work as that component of the force moving the object multiplied by the distance moved. This corresponds to interpreting the equation W equals Fx cos theta as W equals F cos theta multiplied by x. In our example, the component of the force that is actually doing the moving is 5 newtons, and this multiplies by 8 meters to provide the same answer as before. But whichever version you prefer, they both follow the same recipe. Take one vector, find its projection on the other, that means how much of it is acting in the direction of the other, and multiply by the magnitude of the other vector. That recipe describes a form of multiplying two vectors. It's called the dot product. In general terms, that is for any two vectors, not just for calculating work done, the dot product of vectors A and B is written as A dot B and can be defined as A dot B equals AB cos theta. Notice that whether you interpret that as the projection of A on B multiplied by B, or the projection of B on A multiplied by A, it's still just AB cos theta. Armed with this new notation, and noting these correspondences, we can write our familiar expression for work done in terms of the vectors for force and position. So if we call the displacement vector r, because lawn rollers might tend to move in the x direction, but other things might not, then W equals F dot r. And what happens if the value of the force changes along its route? Then we need to chop up the route into infinitesimal lengths dr, along each of which the force can be assigned a constant value, and integrate, so that W equals the integral of F dot dr. Let's investigate properties of the dot product by returning to the example of work done. The more aligned the force with the direction of travel, the greater the work done. This is taken care of in the equation for work done using the cos theta. When the two vectors are aligned, theta is 0 and cos theta is 1. In contrast, for a force at right angles to the direction of motion, theta is 90 degrees and cos theta is 0, leading to no work done. As theta is reduced from 90 degrees down to 0, so cos theta increases and more work is done. So to finish, notice the following things. The dot product is a scalar quantity, even though it's produced from vectors. This fits with our knowledge that work done is a scalar and force is a vector. The dot product increases with increasing magnitudes of the two vectors. And the dot product also increases the more aligned those two vectors are. Pushing a lawn roller horizontally will move it quicker.